In the first module of Foundations of Finite Element Principles, we begin with the assumptions necessary to use a linear static solution. We describe the overall process of building, solving, and analyzing a model. And then we introduce the stiffness matrix of a simple 1D element and explain what the transformation matrix is. Let's take a look at just a quick sample of the theoretical as well as the application videos.
Meshing the given geometry. Now here is where we will devote a significant amount of our time throughout this course into studying different types of meshes and applying some initial thoughts and trying to make decisions about what mesh works better for a given problem. So in meshing, so for example, let me draw, to make my point clear, let me just draw the outline of a gear tooth, for example. So suppose this is a geometry which we can call as you can get this from a solid model, and you want to analyze this basic profile. So meshing could mean dividing this geometry into some elements. Okay, so each block would be termed as an element, and this element, okay, so let's call this as E. E is an element. So meshing would involve dividing the geometry into smaller regions known as elements, and these elements are connected by nodes and the loads on the structure would be applied at the nodes.
Here you can see that even though I selected the geometric face to create the boundary conditions, these boundary conditions are applied at the nodes. So if I had a refined mesh here, I would have significantly more constraints. If I had a much coarser mesh, I would have many fewer constraints. And the same is true for the distributed load. If we look here, the distributed load is applied to a surface. If we go back to the input file, this distributed load is applied to a surface. This surface is defined as an element surface for the distributed load, and it's displayed right here. In Module 2, we will begin by assembling a global stiffness matrix for a problem with more than one element using the direct method introduced in Module 1. We will then discuss nodal degrees of freedom for line elements such as rods and beams, and expand this to 2D plate elements as well as 3D solid elements. In addition, we will also have a brief discussion on how to choose elements for certain applications and discuss boundary conditions and constraints.
So here is our global system in which we know something about this system. And what is that? We know that the displacement U1 is actually 0. The physical interpretation of this fixed end is that U1 is equal to 0. So we will call this as our boundary condition. U1 equal to 0 is the boundary condition. When you substitute the boundary condition into this matrix, we see that since U1 is 0, the terms that are associated with U1 will not be used in solving for U2 and U3. So what that means is application of boundary condition gives you what is called as a reduced system. Reduced system, and the reduced system in this case is 15, -5, -5, 11, multiplying u2, u3 equal to 0 and 100. The thing to note is that the reaction force does not depend on the reduced system or is independent of the reduced system.
Okay, now to continue the discussion, we're going to use both shells and beams in the same model. So I'm not using symmetry anymore. This is the full length of the beam, and we're going to define our boundary conditions and our constraints and our loads just the way that we did before, considering that we have shells and solids. Okay, so that's our load, and right in the middle of the beam, and now let's define our pin constraints. We'll do the solids first. So we want to constrain in the z, and we want to constrain in the y, allowed to translate in the x direction. And we don't need to define rotations because, again, rotational degrees of freedom are not defined on those nodes. And then on the shell side, we define it just like we did in our shell model. So let's do our rotation. We want it constrained in the z, constrained in the y. We want it to translate along the direction of the beam. We want it to be able to rotate about the y direction, but have the other degrees of freedom of rotation constrained. That is not what we want. As you can see, the displacements are astronomical. We've got 5e to the 7th. So what's going on here is that we have a discontinuity here where rotational degrees of freedom are defined for our shells, but not our solids, and we've developed a hinge. And of course, this is an extreme example of this case, but again, I wanted to illustrate to you that when you connect shells and solids, if you just connect the mesh, you may inadvertently create some problems in your model.